All right, in our last video, we looked at alcohols and going to the alkyl bromide, and we specifically learned that we could do primary alcohols to the desired alkyl bromide using HBr, and this is going through an SN2 type mechanism. Now, the issue though is that we have this alkene, and alkenes also react with HBr. So we know that if we have an alkene in the presence of HBr, we're going to get Markovnikov addition of that bromide there. So this side reaction is saying that this functional group isn't really compatible with HBr. So what happens is we end up getting just a gross mixture of brominated products. This would be racemic. We could also see where the alkene reacts. And perhaps we'd have some where the OH hadn't reacted yet. We're just going to get this, hot mess of products. And that's because alkenes can undergo side reactions. I'm going to make another note here that also ethers also have side reactions with strong acids. So both of these, so we're going to write alkenes and ethers, and you'll keep learning more about functional groups and which ones are acid sensitive. But alkenes and ethers are not compatible with HX. In the case of the ether, and we will be diving more into this, but you could imagine, we've seen this before, where we could protonate and this is where our Br minus could come in, and it could kick out this alcohol. We just made it a good leaving group and kick out that alcohol, and so essentially we could end up getting this alkyl bromide. Now, I bring this up because this is really talking about a new realm for us, which is this functional group compatibility, which is a really cool topic, and it's why we have to learn so many reactions. So we're really starting to dive into this. So functional group compatibility. We really want to find reactions that give us the product we're looking for, but don't affect things in the reaction that we don't want it to touch. We want to keep that alkene, but instead we get side reactions with a functional group. And this isn't desired. So there's tons of different ways we can turn the alcohol into a leaving group. And that's what we're going to learn in this video today. And then by the end of the video, you'll be able to know which one to choose under certain circumstances. All right, so this alkyl bromide didn't work with HBr. But what you can do is you can use a reagent called PBr3, so phosphorus tribromide. And this works really well and does not interact with the alkene. Let's draw out the mechanism. So we have phosphorus and we have 3 bromines. The alcohol is going to attack the phosphorus. Phosphorus is very oxophilic. And we have 3 bromines here. One of them is going to leave. Okay. And so from this step, we end up having our alcohol that is added to our phosphorus, which has 2 bromines attached. This is now a really good leaving group. really good leaving group. And so what's going to happen next is we can take our Br minus and we're just going to kick out. This is the Br minus that we kicked out. Here it is. And we're going to kick out this leaving group. Now this does not react with the alkene, so everything's good. So PBr3 is a great way to introduce a bromide, especially when you have acid-sensitive functional groups. Now you could always use this instead of worrying about HBr, which can also make carbocations and then do rearrangements. So this is one way that we can make this alkyl bromide. Now I want to highlight another thing. If we have a tertiary alcohol though, okay, PBr3 does not work well. So let's write this out. It does not work with tertiary alcohols. And that's okay because we know that we can use HBr in this case. Okay, so HBr, we could get our desired SN1 product, right? So this would be going through an SN1 mechanism. But if you tried to use PBr3, there would be no reaction. So notice here how not only is it sometimes we're looking at can it react and can it make the product, but like we showed in the previous slide here, sometimes we need to think about this functional group compatibility. But as you practice, it definitely gets easier to spot these things. Now, the reason that this doesn't work with tertiary alcohols is because notice here in the mechanism, in the first step of our alcohol adding, we're doing this SN2 type addition. So this alcohol is attacking this phosphorus. So if we have a tertiary and it's really bulky, so this alcohol here is very bulky, this would make it a lot worse at trying to attack this huge phosphorus. This is huge with 3 bromines that are huge. They're humongous. And so for it to get in there and attack the phosphorus, it's going to be a little unlikely. So for tertiary, this does not work. Now, another really great leaving group is a tosylate. And tosylates are sulfonate esters. So let's walk through the mechanism of this reaction. Notice here I have a tertiary alcohol, and this can work. Part of this is because the size of our nucleophile, although the nucleophile is the same, our electrophile, it's easier for this to attack. So when we think about the mechanism here, we need to look at what all we have. We have tosyl chloride and we also have pyridine. Let's draw out pyridine. Pyridine is a nitrogenous base. It's a 6-membered ring, and it has that lone pair. And we've talked about this lone pair. It's not in a p orbital. It's an sp2 orbital. Now, we can use this as it's a weak base. It's a weak base. Now, it's not strong enough to deprotonate the alcohol immediately. And you can go back and look at the appendix that we have at the top of the course. And you can see here that on the second page, you can see what a protonated pyridine is, which is around 5, a pKa of 5. All right, let's walk through the mechanism. So we're going to take our alcohol and we're going to attack this tosyl chloride. So tosyl chloride looks like this. It's called tosyl chloride because toluene is a solvent. You don't have to draw this part, but toluene is benzene with a methyl, so this is toluene. Okay, and then tosyl chloride has that TO from toluene, and then the chloride is here. It's also a sulfonate ester, which is where the S comes in. I know some of these words can get, they seem kind of funky, but with time it'll It'll be more fun. It'll be like a little party trick. You'll know all of these random organic chemistry words. All right, so we've got our alcohol. We're going to attack the sulfur. The chlorine here is going to be our leaving group. This works even though we have a tertiary, and that's because this electrophile is a lot better of an electrophile. Also, it's smaller, it's easier for the alcohol to get in. And we only know this through experimentation, but this is a tried and true method for a tertiary alcohol. So we're going to have our sulfur group, our sulfonate ester, okay? And we've got our toluene. All right, now we're going to use our pyridine, which is that weak base. It's going to pick up this very acidic proton there. And then now we're going to have our desired tosylate, our desired product here. I'm going to write TS. This is equal to that huge leaving group, this sulfonate ester. You are welcome to write TS as your product there, but you do need to draw out the structure if you're drawing the mechanism so that we can show that leaving group leaving. So we also had Cl minus leave, and when you look at this, we've now protonated that pyridine. So what happens when we go from our to our product, we have our pyridine hanging out as a pyridinium salt. So we've protonated it, it's picked up that proton, and there was that chlorine that left. So we had this Cl minus leaving group, and so we have this pyridinium salt that hangs out. So pyridine is a weak base. It is used to, I call it a mop. Mops up the HCl. You don't want HCl hanging out in your reaction. You're choosing a sulfonate ester to add to this alcohol, sometimes in case you have a functional group that doesn't like HCl or doesn't like HBr. You get much cleaner reactions when you use pyridine here as a base. So this is one way that we can take an alcohol that's tertiary into an alcohol with a leaving group, and our leaving group here is this tosylate. Now there's other sulfonate esters that we can use. So this is why we use the tosylate, because we couldn't do a tertiary alcohol when we were using PBr3. The next thing I want to think about, though, is how good of a leaving group are all these things? So when we look at this relative rate of a leaving group, this makes sense. Fluorine is not a good leaving group. Chlorine is okay. Let's put this as at 1. And as you go up to bromide and iodide, you are making it a better leaving group. If you were to protonate an alcohol, make it water, it's a pretty good leaving group. Check these out. These are our sulfonate esters, and these are really good leaving groups. And that's because the conjugate acid here, okay? So if we think about this conjugate acid, it's very stabilized by resonance, okay, when we make this leave. These are very acidic conjugate acids. All right, so with this knowledge, not only do we know that these sulfonate esters, they work with that tertiary alcohol, but they also are a really good leaving group. So we should explore this a little more. Let's look at mesalates. Let's go ahead and run that reaction. How would you do this? Well, you'd also use mesyl chloride, similar to the tosyl chloride. These are very similar reactions. So let's just walk through the mechanism here as a nice little practice. So we've got a methyl group, we've got our sulfonyl group with our chloride leaving group. Our alcohol will attack the sulfur. It'll kick out this chlorine. Now notice here, we do have this chiral center. So if you started here with this optically active alcohol, we didn't change the center there. We didn't draw any arrows showing that inverted, and it doesn't invert. Now we can take our pyridine, we can deprotonate this very acidic proton to get to our desired mesylate. So this is a mesylate, MS. Now MS is very different than ME. Remember, ME, we know that that's a CH3 group. So this MS is this CH3 bound to this sulfonate. So this mechanism is really similar. Your pyridine is now protonated. This is simply just acting as a base, and then you have your Cl minus, so you've got this pyridinium salt. So mesyl chloride is used to add your mesylate group, and then pyridine is just, again, mopping up that HCl. Now I want to make a special note here, put a star here. We do not flip that stereocenter because there were no arrows drawn at that chiral center. So that's one way to kind of remember that that doesn't flip. Let's learn another way to make a leaving group, and this one is using SOCl2. And so you're going to be going from an alcohol to an alkyl chloride. Now this really only works, this works the best for primary alcohols. So just keep that in mind. Because you can get rearrangement. Can get rearrangement if you have secondary alcohols with beta branching. And that's okay because you can always just use a different leaving group if you have a secondary alcohol. So I want to show you this mechanism though, because SOCl2 is a really useful chlorinating reagent. So let's just take a primary alcohol, and we have SOCl2. Thionyl chloride looks like this. And we're going to take our alcohol and we're going to attack our sulfur. We're going to kick out our chlorine leaving group. Now it still has a hydrogen attached. We also have pyridine present in this reaction too, typically. You're going to deprotonate it with pyridine. Okay, now you have this really good leaving group here. What's going to happen is we kicked out chlorine in this first step. So we're going to have Cl minus come into an SN2 reaction here and kick out this group. And this is one way you can access alkyl chlorides. Again, it works best for primary alcohols. You can use secondary, but not if you have beta branching. It doesn't work very well. You get rearrangements, or it can get rearrangements. So this is just another way to turn an alcohol into a leaving group. Let's look, though, at this whole idea about stereochemistry with leaving groups. All right, so if you have a chiral alcohol, and this is optically active, what if you wanted to keep your leaving group on the same side there? Okay. Now, what if you wanted to take this optically active alcohol and then you wanted to switch the stereochemistry? So what if you wanted to invert it? Maybe you wanted this carbon with a leaving group. This is really important when you're dealing with like SN2 or E2 reactions where you want a specific optically active compound. And so we really need to think about what leaving group we are going to install. So let's consider this. So if we use mesyl chloride with pyridine, I'm going to write PYR for pyridine, or you can take tosyl chloride and pyridine. We know that we're going to get this leaving group on that wedge here. So you can have a mesylate, MS, or you can have your tosylate. And notice how that didn't switch, like we've gone over the mechanism here. Now, in one that you can do to get that leaving group back would be that PBr reaction, PBr3. And in this case, we know that it goes through an SN2 type mechanism. That means our bromine will be back. And so what's really neat about this is you can start with this optically active alcohol, okay? And in this case, we have this S. Now, if you want to have your leaving group in a different position, you can change which leaving group you turn it into. Here, we've inverted it. That's because this reaction undergoes an SN2 at that stereocenter. Now, this top, it stays the same. So it's the same stereochemistry. SN2 inverts. Let's walk through some practice problems so we can practice this idea about taking our alcohol, turning it into a leaving group, and knowing what kind of leaving group and where we want it to be. What's your favorite leaving group? Oh, you like tosylates. Well, that's interesting. You do? Very cool. They don't switch the stereocenter. So let's practice this with E2. And when we think about this, we're trying to do an E2 reaction, and this is going to take more than one step to do. Because we know that one, we need to make this a good leaving group. Remember that OH minus is a bad leaving group. And this is why we're doing this, to turn it into a good leaving group. So this is a bad leaving group. So the first step, we're going to turn it into a good leaving group. And then in the second step, we're going to add a strong base to do the E2 reaction. So let's say we were to take PBr3, okay? And then our second step, we're going to do an E2 reaction, sodium methoxide. Notice here how we're adding, essentially we have two different reactions happening sequentially, and we are getting our product, but notice how the knowledge that you're learning about these reactions are building. This is how it starts to feel kind of complicated. The best way to approach a problem that's written like this is just go stepwise. So if you approach this problem, and you've got your alcohol, and you see, okay, I've got a secondary alcohol, and my first step is PBr3. So what you're going to want to do is then you just do the first step. You don't even have to be concerned about what the next step is. It's really easy to get overwhelmed, especially when we start doing reactions that have like 3 or 4 or 5 steps involved with them. So just go one at a time. PBr3 inverts that stereocenter, and it replaces an OH group with a bromine. Cool. So there we go. We replaced it and we inverted it. Now we go to step 2. So this was step 1. And now let's go to step 2. So for step 2, we know that we're going to do an E2 reaction. This is a very strong base. We have a secondary alpha carbon. So E2 is preferred. Now, when we're looking at this, we know we have a small base, and our work with E2 reactions reminds us that it can take a proton from any of the beta carbons, and it will prefer to take one that is going to give it the more substituted product because this is a small base. So although there's a beta carbon here, it's a small base. So it would rather take it from an internal beta carbon to give you a more substituted alkene. So small base, remember it's going to give us the more substituted alkene. Okay. Well, with that knowledge, I'm going to erase this beta on the end. We're not going to take the proton from there. Now, the next caveat of E2 reactions that is fun, I don't know if you want to call it that, but remember, if we have our alpha and our beta carbon, if they are chiral, then you need to worry about, then you need to look at the anti-coplanar rule. And this is because it could give you a specific type of alkene. And so when we look at this, we do have our alpha and beta carbon are chiral. So what we need to do is we need to reorient this molecule to have our proton and our leaving group anti-coplanar to each other. So let's rotate this. There we go. What I like to do is I like to put my leaving group and my proton on the plane of the paper. And then I like to fill everything else in. I think it makes it a little easier. Our proton here is on this beta carbon. This is the one that we're going to take. And then here's our leaving group on our alpha. And as we rotate this, we have our bromine back. So we're going to pull it forward. That means that this methyl is now going to be going back. This methyl that we have here on the beta carbon is coming forward. That means that proton here was back. So we're going to take that proton and pull it towards us so that now this proton is in the plane of the paper. That means that that methyl gets pushed up, but it's still coming forward. So it gets pushed up. And again, if you're having a hard time seeing this, I highly suggest building a model. This cyclohexane group will then be pushed back. And as we look at this, when we do our E2 reaction, so we've got sodium methoxide, OMe. When I deprotonate it, I'm going to push down to make a new carbon-carbon double bond and kick out bromine. And when we do this, we're going to make an alkene where the cyclohexane group and our methyl, they're both dashed, are going to be on the same side. So let's draw in our product here. So we have our alkene, okay, and then we have our methyl and our cyclohexane on the same side. This one also has a methyl. You could go one step further and say, what kind of an alkene have I drawn? Do I have an E or a Z alkene? Let's review that again. So when you do E or Z, draw your dotted line in the middle, and then I like to underline or circle your higher priorities. Methyl wins over the hydrogen, so this is higher priority. And then on the left side, our cyclohexane is a higher priority than the methyl. Both of these are on the same side, so this would be a Z alkene. Notice here that we went from an alcohol, we made it a leaving group here with the bromine, then we did an E2 reaction. The only reason then we had to dive into the anti-coplanar was because we had an alpha and a beta carbon that were chiral. These problems can start to they really build upon each other. And so if you go stepwise, that is, in my opinion, that's the best way to do it. That way I don't want you to jump over to step 2 and then start worrying about anti-coplanar. You may not even need to. In this case, alpha and beta carbon were chiral, so then you need to look at anti-coplanar. Let's do an SN2 reaction here. So we're going to go through a couple examples here. So on this top one, let's use tosyl chloride with pyridine. And then for our second step, we're going to use a good nucleophile. Let's use CN- as our nucleophile here. So in the first step, we know we're going to take this alcohol. We're not going to switch the stereocenter. We're going to add our tosylate group, okay? And then on our second step, we're going to do an SN2 reaction. So this is step 2, and here we're doing SN2. We know that we're going to invert this. So our step 2 has sodium cyanide. And so our desired product here is going to be the CN group going back. Now, what if we wanted to form a substitution product using the same alcohol, but instead we wanted that group to be coming forward? Again, we're going to start with this optically active alcohol. Well, we did learn a leaving group that would flip this. So if we start with this optically active alcohol, in order to get this nucleophile on the same side, we're going to need to switch our leaving group. We're going to need to first make it go back. So if you were given this problem to fill in the reagents, your first step is going to be making this alcohol leaving group that is going back. Because when we do the second step with the SN2, we're going to invert it. So maybe now you can pause the video and try to see which of the leaving groups you want to use for this reaction. All right, let's jump in here and solve this together. So we're going to use PBr3. Remember that PBr3 will take that alcohol and flip it. It's an SN2 type reaction. We're going to get the bromine going back. And then for our second step, we know that we added this CN group, so we're going to add sodium cyanide to do that SN2 reaction. Notice here how it's really cool. We can use this leaving group capability to change which stereoisomer we get for this substitution. And so that's it for this video, where we really looked at taking alcohol, turning it into a leaving group, and utilizing it in multi-step reactions. We've also learned why we need different leaving groups for functional group compatibility. And then we went over practice problems with E2 and SN2. And that's it for this video, and I will see you in the next video.